and display from the University of Melbourne here, and he's going to talk to us about light-emitting sectors.
Okay, so thank you all for coming and being prepared to listen to me. I'll do my best to not be too boring for the next hour. So this talk is based on some work that I've been doing with David Morrissey at Triumph, which we finally got finished early this year. The archive number is given there if you want to look it up later. The outline of the talk takes the form of, well, 90% of the outlines of talks that I give at least. I don't know about other people, but I find that it always seems to break down to the same sort of structure. We have an introduction motivation. We talk a little bit about the model in question. We talk about the phenomenology, which in this case corresponds to current and prospective limits from a variety of experiments, but in particular electron and proton fixed target experiments. And then finally I will give some conclusions. So let me start with something that is almost insultingly simple. This diagram here represents our current understanding of the universe, dividing into stuff we know and stuff that we don't yet know. And the division between the two corresponds to a line which increases the, for larger values of m, the point at which we know stuff about corresponds to higher couplings. Simply because if something is heavy, it is harder to produce it. We need to have a stronger coupling to stuff that we already know about. What does that mean? Well, it means that if we assume the coupling of whatever is new is an order 1 coupling, such as, for example, a gauge coupling, then we're interested in new physics that is TeV scale. That is the kind of stuff that we look for at the LHC, the kind of stuff that I have done most things before this project looking at. But if we want to look at something, that doesn't mean that's the only thing we can look for. If we allow our coupling between the known physics and the new physics to be a small number of the order of, say, 10 to the minus 3, then this allows us to have new physics that is of the mass scale of a GeV or less. In other words, that we can have like physics as long as it is in some way hidden from the standard model through a small coupling. And there's a number of reasons why people have thought about this. I've picked 4 here, but there are others if you want to dig into things. These just seem to be somewhat irrelevant. One that I will draw attention to, because I will come back to it in some more detail, is the anomalous magnetic moment of the muon. As is well known and is well established, there's this 3.5 sigma discrepancy between the measured value for the anomalous magnetic moment and the theoretical prediction. And one way you can get this is by coupling to some new physics, comes to the muon. The general parameterization of that contribution takes this form, or to put it another way, if your coupling is of the order 10 to the minus 3, then your mass of the new physics is of the order of the GeV, precisely what I was talking about before. Other things that people looked at, there's a lot of dark matter anomalies that might point towards new physics at the order of 1 to 10 GeV. Here are some direct detection possible hints that are in some tension with Lux now, but they weren't when I first made this talk. And then there are this signal at the galactic center in low energy photons, well, low energy GeV photons. These are sort of experimental reasons. On the somewhat more theoretical side, one reason to consider light stuff, and in fact the first reason that we started thinking about the particular model in question, is the concept of a hidden valley, a theoretical construct where you have this light physics that couples weakly to the standard model, but you also have a heavy sector which couples more efficiently to the standard model, and which also couples efficiently to the light sector. So that you can reduce the light sector at the LHC by going via the heavy sector. Another thing that has grabbed some people's attention of late is noticing that the dark matter mass, the dark matter relative abundance is comparable to the abundance of visible matter. There's a factor of 5 or so between the two. And if you assume that there's some symmetry that enforces the number of dark matter particles in the universe to be the same as the number of visible particles in the universe, then the observed ratios of abundances today gives you that the mass of the dark sector should be of the order of 5 times the mass of the proton, which is again in this GeV scale. But there's some order 1 wiggle room in these sort of models. Now the other part of the title that I talked about, you can go away, is fixed target limits. Maybe you can't. Okay, fixed target limits, the other part of the title, are an example of the intensity frontier. And these are models where we have a high luminosity and a low, or another way, controlled backgrounds. The high luminosity allows us to probe small couplings, but to get these low uncontrolled backgrounds, again, restricts us to low masses. In other words, precisely the type of thing that I'm talking about. And these experiments take the rough schematic form like this. You have some beam that comes in and hits your fixed target here, which is stationary, hence fixed. Then you have some block of shield, possibly a decay volume, and a detector that is a long way away from the target relative to its transverse size. And the thing about drawing attention to this is to ask what sort of details of this low energy hidden stuff that they are sensitive to. So you have your production of an initial hidden sector state. It will then undergo some prompt decays in general through the hidden sector. So we have possible relative dependence on production and prompt decays. But then the fact that we have this shield, and this shield is fairly macroscopic in distance, means that we need to produce some state that is either long-lived or stable, that can travel this macroscopic length. And then anything we say about these hidden sectors at these experiments is going to be highly sensitive to what this particular state is and how it decays, or if it decays. Then finally you look for a signal which can either come from its decay into the visible sector or from its scattering with the visible sector. So we're also going to care about exactly what's going on here. In short, the questions that we end up looking at in these models and these experiments: what is the long-lived state that will give us this thing here? How is it produced? What exactly is the details that are going on here? And in particular, are we talking about on-shell processes or off-shell processes? That will have a lot of importance to the type of limits that you can set. I'll put that in a little bit more context later when I start talking in details of these experiments as well. And how does it decay or scatter? Now, let's start moving a little bit more towards the precise model that I want to talk about. And let's ask how we can have something that is hidden from the standard model. Now, I can always do it by tuning some coupling to be a small number, but there's sort of a natural, I can also, but in general, if I have a hidden sector, what it means is that I have some stuff that is neutral under the standard model gauge charges, otherwise, by definition, it wouldn't be coupled. And there are three renormalizable couplings between the standard model and gauge neutral operators, which are commonly referred to as portals. And when it comes to thinking of portals, our choices are a vector portal here, where we have a coupling between the standard model hypercharge gauge boson and some new muon gauge boson. That's a kinetic mixing between the two states. The nice thing here is that the state that we couple to, the photon, is massless, and the coupling that we generate is proportional to electric charge. So this is a fairly easy thing to probe, relatively easy thing to probe. We can have a Higgs portal coupling. This is the Higgs scalar. H dagger H is a gauge singlet. And then phi dagger phi, some other scalar, that's also a singlet. The main problem with this is that the LHC is the only place that we produced Higgses, at least that we can do say measurements about. So anything we want to say about this particular portal coupling is going to be dependent upon what measurements we can make at the LHC. And the final possibility that we can do is we can write down a neutrino portal, a coupling between the left-handed electron doublet, the left-handed lepton doublet, the Higgs field, and then some right-handed neutrino, or more generally some Majorana fermion. This also involves coupling to a massless or near massless state, but it's much harder to produce because it's much harder to produce the neutrino, or more precisely to measure the neutrino, I should say. So for this reason, we're going to focus in this talk entirely upon the first possible portal, the vector portal. And I'll say one other thing before I move on, which is that the coupling here, epsilon, can be arbitrarily tuned in any way, but if you think of this as coming from a loop-generated process from, for example, some heavy states which are charged under both the standard model hypercharge and whatever this new muon gauge symmetry is, then at one loop, the natural size you generate for this parameter epsilon is 10 to the minus 3, the number that I've mentioned twice already, and that I'll mention again on this slide, which shows, well, two things. First of all, that I'm by no means the first person to talk about this. There's a huge literature of people looking at what you can get when you have a massive vector boson, or even a massless one, but I won't talk about that here. A massive vector boson coupled to the standard model through a mixing, a gauge kinetic mixing with the hypercharge gauge boson. And this plot from a review paper last year shows a large number of exclusions over a range of masses for this gauge boson from 10 to the minus 15 electron volts up to a TeV. And this parameter here, this is the kinetic mixing, I have used epsilon, but some people use chi, between 1 and 10 to the minus 50. However, if you look at 10 to the minus 3, if you look on this line here, and if you look at scales around about a GeV here, this space is relatively unconstrained. So this is a natural place to start looking at these things, and to say a few more details about this. There's also some previous fixed target experiments here that I will also say more about. In fact, we'll start saying a little bit about them here. Existing fixed target experiments looking for light kinetically mixing gauge bosons. These searches generally make one of two assumptions, which is reasonable assumptions from a minimal perspective. They either assume that the light gauge boson decays to standard model lepton pairs. It could also decay to mesonic stuff, but that's somewhat harder to discriminate from backgrounds. So this is a typical, well, this is the most up-to-date example of what those limits look like, taken from a review paper from last year. We have a large number of beam-lip experiments here, CHARM, E70, E141, E137. And the general feature here is that these set limits at small masses, these masses are less than GeV, and at small kinetic mixing parameters, 10 to the minus 5, 10 to the minus 6. This is sort of motivated as the absolute minimum model. If you have this muon gauge boson and nothing else, this is the signal that you will get, because the gauge boson has nowhere else to decay other than through the kinetic mixing back into the standard model. The second possibility is that it decays invisibly, strictly invisibly. This gives you somewhat weaker sets of limits. The kinetic mixing parameter here, 10 to the minus 3, 10 to the minus 4. Limits come from Chinook experiments, are the strongest, LSND here, and a few other places. These sort of searches are motivated when you have dark matter. The idea is that the gauge boson is decaying into the dark matter particle, whatever it might happen to be. And again, it's sort of a fairly minimal model if you have light dark matter that couples to this gauge boson and nothing else in your hidden sector. So it's always possible that the hidden sector is minimal and that you just have the gauge boson sitting alone by itself, very happy and lonely. But you could also have a non-minimal situation. There's, in general, no reason why not. You can have some friends, you can have scalars. In particular, you can have Higgses to give the gauge boson a mass. For a muon gauge boson, you can give it a mass through the other mechanism, the Proca mechanism, where you can just write down a mass and then generalize it in an appropriate way to make a gauge invariant. But having a Higgs is sort of nice, especially now that we know that Higgses do exist, having found one. Or we can have additional fermions other than just the dark matter state. Once we allow this possibility, we have this qualitatively new type of signature that can show up for these models, where we produce the hidden vector, and then rather than decaying to something that is just invisible, or directly decaying to the standard model, it decays back to the standard model in a two-step process, decaying first to some other hidden sector states, that in turn decay to visible particles. And if we think about what this, generally speaking, can mean, we can find four classes of scenarios, four classes of models. We can have the two that we started with, where we have a direct decay into the visible sector, or we have an invisible decay to some state that, whatever it is stable or has other invisible decays. The precise details aren't important, it's just that this thing doesn't lead to anything that we can see. But we can also have the situation where the gauge boson decays to scalars that themselves ultimately decay back to the visible sector, or to fermions that ultimately decay back to the visible sector. And these have been much less studied. In fact, we're not aware of any previous studies on this scenario here. There is one previous study we found on this situation, this paper here by Schuster, Toro, and somebody else that I can't remember offhand. But we're going to expand on the types of limits set on these models fairly substantially. The other thing to draw attention to here is that in this situation, the gauge boson is forced to be the long-lived state that we look for at these fixed target experiments. Whereas here, it is other states, scalars or fermions, that will be the long-lived states that we look for. And so the nature of the relationship between the kinetic mixing parameter epsilon and the types of limits that you set will be different.
Sorry, so for the last mode, what is, the alpha plus minus is not a firm.
So yes, so I'm being very, very schematic here. More precisely, as I'll come to in a moment, the lightest fermion in the model that I will consider will be absolutely stable.
So it'll be like the
It will be
dark matter case?
so you have to annihilate to you have to decay to a heavier fermion
Oh, I see.
that then decays to L plus, L minus, and the dark matter candidate. It might be possible to write down a situation where that's not the case, and then you have a different decay, say to a lepton plus a ion, for example. I can't think off the top of my head if you can write down a model with that. But as I said, I'm being very loose and sort of sketchy when not sketchy, schematic when I write this down. But the question then becomes, can I construct a model with all of these 4 decay modes in it? And the answer is no, end of talk. The answer is no, because we'd actually already built a model that does this, although we didn't realize it at the time. So in this previous paper that we had looked at a hidden valley type model, this model is a supersymmetric model. So it has both hidden scalars and fermions as a requirement of supersymmetry. You can add R parity so the lightest fermion is stable, which guarantees that you have an invisible decay. Or as I was just saying right now, you don't have to add this R parity, although that gives you all of the usual supersymmetric issues that you have to deal with. The specific model is the minimal supersymmetric model with a U1 gauge symmetry. So the matter content, you have a vector field plus its associated gaugino, and you have 2 Higgses with 2 Higgsinos. And this is the minimal anomaly-free content that has a U1 gauge field that is hidden, has a hidden sector that gives the U1 gauge field a mass. Once you break that U1 gauge symmetry, the fields will of course mix. So you have a massive vector field, which I will call Zx, 3 scalars, which I will take to be 2 real and 1 pseudoscalar, which amounts to assuming that CP is a good symmetry in the hidden sector, but this is this is a weak assumption for 2 reasons. First of all, CP is not spontaneously broken by the scalars. And secondly, the limits on CP are fairly irrelevant to limits on CP from the visible sector because the 2 sectors couple only weakly. They couple only through this kinetic mixing parameter. Modular 1 statement I'll make later. And you have 3 Majorana fermions, including therefore heavier fermions that can decay to the lightest stable one. And the parameter space of this model over the MSSM model, which of course has the 100-odd parameters new to the standard model that it usually does. On the supersymmetric side of things, 3 parameters preserve supersymmetry, the gauge coupling, Gx, which I will throughout take to be equal to the hypercharge gauge coupling. The kinetic mixing parameter that is extremely important, and that I've talked so much about already. There's a Higgsino mass as well. And then you have 3 masses and 1 ratio of Vebs on the SUSY breaking side of things. The vector boson mass, superscalar mass, the gaugino mass, and the ratio of the Higgs Vebs, which I'll call tan zeta, by analogy to tan beta in the MSSM. I'm not going to say a whole lot about, well, in fact, I'm not going to say anything about the supersymmetric generation of these parameters beyond the following. If supersymmetry is broken only in the visible sector, and the hidden sector does not directly couple to the SUSY breaking sector, then all of these masses will be epsilon suppressed. So for TeV scale superpartner masses, it's natural to get GeV scale masses in the hidden sector. But I'm actually going to take a phenomenological approach and let all of these parameters be free parameters and see what happens when I do that. So the thing about this model is that, as I've said, it's minimal. It has all 4 of these simple decay modes. It also has some more complex decay chains that are possible, although, again, I'm not going to talk about that in this talk. In fact, we haven't really looked at this in any sort of detail at all. Now, you can think of this model on its own merits and just study it as, I've written down a model, what does it look like? But you can also think of this, because it has the feature of containing this and it's also minimal, as a framework to examine general hidden sectors. Where by general hidden sectors I mean hidden sectors that involve a U1 gauge field that kinetically mixes with hypercharge. So in that sense, we should perhaps not think of this in detail as the model itself, just something that lets us examine all of these different phenomenological types of behavior in one simple unified framework. Now, I said I was going to look at these parameters in general, but that's actually not entirely true, because it's still a 7-dimensional parameter space. Even if I fix the kinetic mixing, that's still a 6-dimensional parameter space. It's kind of a lot to say anything really concrete about. So instead, I'm going to pick 4 benchmark slopes, 4 points in parameter space where I fix the ratios of the masses in the hidden sector, but then it'll give me one common mass scale to vary, which I will take to be the vector boson mass. And each of these 4 benchmark slopes will correspond to one of the 4 decay patterns that I mentioned. So the first one is the one where the gauge boson has decayed to the standard model. The vector is too light to have any decays to the hidden sector. Generically speaking, this is true whenever the gauge boson mass is the lightest of the masses in the hidden sector, just kind of obvious. So this is going to be very, very, very similar to the most common assumption that is made where the gauge boson decays to electrons. There are a couple of new things, specifically the ability to produce hidden sector states other than the gauge boson through an off-shell vector will lead to some new and interesting limits. I've talked about how we produce this hidden sector in the sense that we're going through the gauge boson, and we can possibly an off-shell gauge boson to get other hidden sector states. It's also, as I emphasized at the beginning, important to consider what the long-lived states in this model are. And generically speaking, there are 3 possibilities: the pseudoscalar, the fermions, and the scalars, particularly the lightest scalar. The pseudoscalar is not, in this particular benchmark, a long-lived state. It can decay through this on-body, on-shell, 2-body decay, pseudoscalar to vector plus Higgs, so that's not going to be a long-lived state. The fermions also turn out not to be long-lived. They can all decay again. 2-body on-shell decays, apart from the lightest one, which is stable, of course. Heavier fermion to lighter fermion plus hidden sector boson of some type. The scalar, however, will be long-lived. If you go back to the spectrum, it's sitting down here at the bottom. It has nothing in the hidden sector to decay to. Its decays to the standard model will be suppressed. I'm going to say a bit more about this because this is common to 3 of the 4 benchmark slopes, so I'll come back to this point in a moment. The second benchmark corresponds to the other case that has been looked at before, which is where the gauge boson decays invisibly. So the vector has one hidden decay to the lightest stable fermion, which is generically true whenever I have this ordering of the masses in the hidden sector. So the gauge boson mass is the second lightest, and the gaugino mass is the lightest. So the spectrum, which is sketched here, we see the gauge boson, we see less than half the mass is the fermion that it can decay to. As before, we still have new signals beyond those that have been looked at when we produce other hidden sector states through an off-shell gauge boson. And on the question of long-lived decays, it's very similar to the previous case. The fermions and the pseudoscalar have on-shell hidden sector decays. The pseudoscalar specifically decaying to 2 copies of the lightest fermion. The scalar, again, has suppressed decays to the standard model. It is actually heavier than this thing, but not quite enough to decay to it. And again, I will say more about this in a few slides. The third and the fourth benchmarks, slopes C and D, these are the most interesting ones, because these are the ones that give us this new behavioral phenomenology. And benchmark slope C is one where we decay into hidden scalars. And then the hidden scalars must decay to the standard model because they will have no other possible decays within the hidden sector. There are no other hidden sector states that are lighter than them. Generically, this will happen whenever the pseudoscalar mass is lighter than the gauge boson mass. And again, here's the spectrum. Here is the gauge boson mass, and it can decay to these 2 states at the bottom of the spectrum. In terms of what states are long-lived, now the pseudoscalar, again, like the scalar, it has no on-shell decays within the hidden sector. It must decay through this 3-body channel, through the gauge boson, though suppressed also by the kinetic mixing parameter and by the 3-body phase space. And then the fermions, they are also fairly boring, and they just decay promptly. Finally, benchmark D is where the vector decays to fermions, but not just the lightest fermion. They can decay to ones that are unstable. And in particular, I can range it for this particular choice of parameters, that the branching ratio to the final states involving the second heaviest fermion, the next lightest one, is 94%. This pattern of decays is generically will happen when the Higgsino mass is lighter than the vector gauge boson mass. So this ordering of parameters. And here we see the gauge boson can decay to these two fermions. Again, pseudoscalar is, as in case B, not long-lived, it can decay to fermions, but the scalar also is not long-lived because it can decay to fermions. But if we look at this thing here, this fermion can only decay to this thing plus some other stuff, and this other stuff has to be in the standard model. So we're looking at, again, a three-body decay involving hidden sector state going to lighter hidden sector state plus a pair of leptons through an off-shell gauge boson. So this thing can quite easily be long-lived and lead to signals at these fixed target experiments. Now, one feature of this model that comes out of the supersymmetric nature of the model is that I can't just write down a vector kinetic mixing. That cannot be the only coupling I have between the visible and the hidden sectors. There must also be a Higgs boron type coupling. This comes from the fact that if I write down the kinetic mixing, it's a kinetic mixing not of the gauge fields, but of the superfields, the vector superfield X and the hypercharge superfield B, which contains, in addition to this mixing here, a mixing between the two auxiliary scalar fields. Or, once I integrate out the auxiliary fields, this coupling here between the hidden sector Higgses and the visible sector Higgses. Now, there's an overall factor of epsilon on this equation here. So the actual mixing between the visible and hidden sector Higgses induced by this coupling is pretty small, suppressed by epsilon and also suppressed by a ratio of masses. So its effect on the standard model, like Higgs phenomenology, is pretty weak. But it can be very important to the hidden sector, and in particular, it allows a new channel for the hidden Higgs to decay. So let's talk about that hidden Higgs. As the lightest scalar, it has no decays in the hidden sector to other bosonic degrees of freedom. It can decay the hidden sector fermions, which happens in one of the benchmark steps I consider, but in the other three cases, this decay here is not allowed. So I must consider some type of decay to the standard model. There's a full-body decay through two off-shell gauge bosons, but if we are in the situation where the scalar is lighter than the gauge boson, this is relevant, as was shown in previous work here. It can decay through a vector gauge boson loop. This is the only possibility in a situation where you just have gauge boson kinetic mixing, and so this is the one that people have thought about most, well, at all before us. But in the presence of a Higgs mass mixing, you also have this decay happening through this mass insertion here, where we have the hidden sector Higgs mixes into a standard model like Higgs, which then decays through its Yukawa couplings to the standard model fermions. So we'll have an interference between these two decay modes here. Now both of these things are quite heavily suppressed. They're suppressed in this case by 2 powers epsilon, well 4 powers in the once you square the matrix element plus the loop factor. Here by epsilon squared, but also 1 over the Higgs mass squared. So this means that the scalar is pretty much always long-lived, unless, of course, we allow this decay here. That's why the scalar is interesting phenomenology in benchmark slopes A, B, and C. And the effects of the mass mixing can be seen quite nicely in this plot, which shows the decay length of the lightest scalar as a function of its mass for kinetic mixing parameter of 10 to the minus 3. And a few of the parameters also fixed to simplify things. What's going on here is that the the red dotted line, this line here, that is what comes just from this loop decay here. That's the case that's been looked at before. The blue dashed line is what comes just through the mass mixing here. And then the black line is a combination of the two. And you notice that once you're above the pi threshold, the decay is just dominated by the mass mixing decay. And so this leads to quite different phenomenology between the two cases. This case where I have a non-SUSY-like model without the mass mixing, or the one that I'm considering here with the mass mixing. And I will, in fact, in all of my exclusion plots where this is a factor, I will show limits with and without the mass mixing, so you can see the type of effect that it has. Okay. So having gone through the details of the model itself, let's talk about the phenomenology. Let's talk about the limits that I can place based on stuff that's already been done, and on things that have been proposed in the near future. I'm going to start, despite the nature of the title, with some some non-fixed target limits that are kind of basic things you can't ignore, starting with some completely model-independent limits on kinetic mixing parameters. You have two limits. First of all, electric precision limits. The fact that you have kinetic mixing with the standard model hypercharge, well, of course, the hypercharge boson contains the Z boson. So this kinetic mixing will modify the properties of the Z. And if the hidden sector mass is light, what it mostly does is modify the mass, mz. So precision measurements of the standard model Z boson mass gives us an approximate limit of epsilon, must be less than about 0.02. Anomalous magnetic moments. I mentioned already the importance of the muon anomalous magnetic moment and how hidden sector gauge bosons could perhaps explain it. Now this is just an introductory QFT calculation. I've sketched the diagram here, which is just, if you replace this thing with a photon, it's the first one-loop calculation that you ever do. So first of all, we have the possible explanation of the uncertainty in the anomalous magnetic moment of the muon. But we also have limits from the fact that the muon and the electron magnetic moments have been measured quite well. Details given in this paper here. The other thing that I want to talk about are decays from limits from rare decays of mesons, which I'm showing here from the review paper that I quoted already. Limits in the case when the gauge boson decays to a pair of electrons or when it decays invisibly. So this limit here is from a bar looking for decays of the Meson meson decaying to photon plus your hidden gauge boson decaying to photon plus 2 muons. And there are also limits that are harder to see from rare decays of pion and the phi. Similar limits over here, looking at the decays of the upsilon to something invisible and decayon. So these are that's the bar limits in blue there, and projected limits from Bell 2 in the blue line that is not shaded in. So again, we have to consider what these things look like once we consider a more general hidden sector topology decay. And there's an issue here which is related to the decay topologies. So if we have the decay of the hidden gauge boson decaying visibly, for example in the case of the upsilon meson, what you get is this pattern of decay. It decays to photon plus your gauge boson, which decays to a pair of muons, and then one of the cuts that is imposed, the total energy of this system, is equal to the energy of the parent, or the invariant mass reconstructs the mass. So that is one of the tags made on these searches. If it decays invisibly, then what you're looking for is your tag, a photon in this case, plus some missing energy in the event. But if the gauge boson decays to the hidden sector in a non-trivial way, as happens in our benchmark slopes C and D, we get something more complicated. For example, if it decays through scalars, we get this diagram here, which I have actually truncated a little bit by cutting out another gauge boson propagator at this vertex here. So the upsilon decays to a photon plus the gauge boson decays to a pseudoscalar, the pseudoscalar decays to another scalar plus a pair of leptons through an offshore gauge boson, right? And if the scalars are long-lived, then what this looks like in the event, you have your tag, the photon, you have a lepton pair, and you have missing energy. Right? It's not the same as this search here. You won't get limits in this search, and this search here has not been done as far as we are aware. If, on the other hand, these Higgs's decay, if they are sufficiently short that they will actually decay in the experiment, then you have 6 leptons in your final state, which again is different to what's been looked at before and has not been done. The search has not been done. Although I was talking to one of the guys at Melbourne, he said that this should be in the data, it shouldn't be hard to do the search. They just need to find a grad student who needs a project.
What's the branch ratio of this HX to leptons?
Sorry,
So this HX, so you say if they both decay
So
to
this-
leptons,
okay,
you're
so
gonna
if
get
you are
electrons.
below the pion threshold, the branching ratio is 1 electrons by definition. If you're above that, then the branching ratio is quite suppressed by, I can't remember the numbers offhand actually, it's definitely less than 10%. I think it might even be less than 1%. So your limits above that point are going to be cut off, are going to fall off, obviously. But what I'm saying is there's just no limit at all on this search. And so what you end up with, when you combine all these things together in the case of benchmark slope C, is something which is like this, where here's the mass of the gauge boson, here's the kinetic mixing parameter. So we have electric precision, an automatic of the muon of the electron, and then this region here is the equivalent to this region here. The search that comes from, actually it's equivalent to this region here, because it only comes from the invisible decay modes. So what happens here in this region is that the boson decays to photon plus the gauge boson, which decays to scalar plus pseudoscalar, but these things are sufficiently long-lived that they don't decay within the detector, they appear as missing energy. And that's why we have this behavior here on the limit. This is the point where the pseudoscalar decays promptly, above that point, and you actually see it in the detector. There's also, on this plot, some cosmological limits from CMB and BBN that I'm not going to say any more about. They come from the from the scalar decay at late times and Meson of CMB and BBN predictions. In the case that the gauge boson decays to fermions, we have again quite different limits that only come from the bar search for invisibly decaying scalars. Well, pseudoscalars actually, but they can be reinterpreted. Down here you have contribution from both of the fermions, and up here only from the fermion that is absolutely stable. Okay. With that out of the way, let's get on to fixed target type experiments, starting with electron fixed target experiments. So, the ZX couples to electromagnetic current, so trying to produce enough electrons is a sort of an obvious thing to do. And this has been a very important area where people have recast old experiments in order to place new limits on these types of models. This plot here is essentially equivalent to the one that I showed at the beginning of the talk, where you see that there are beam up limits at masses of this gauge boson here, up to about a GeV, a little bit less than a GeV. And kinetic mixing parameters 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. They use a slightly different notation again. Chi here is the kinetic mixing parameter, and this is MZX. On the basis of this sort of limits, there's also been a number of experiments proposed to fill in this empty region here. Right? So the Meson searches, they sort of live around about here. So we have a big empty space. People want to try and fill in that empty space and show either there's something there or these models are all nonsense.
So in these experimental limits, the upper line is because when chi is getting bigger, these decays are becoming prompt? Or
The decays are becoming too prompt. Specifically the decays...
They don't make it through the...
Yeah, they won't make it through the shield. That is exactly what it is. Alright, so this is another, since it was a while ago, 30 minutes ago, that I showed you the sketchbook fixed target experiment. This is it again. Electron comes in, hits target, passes through a shield, and must be long enough lived to pass through the shield. Decays in some volume here to, well, all of the searches here look for electrons, so it must decay to electrons, and they must hit the experiment. This includes all of the past experiments of this type, electron beam up experiments, and most of the ones that are either running or have been proposed. And as I have emphasized before, or indeed as Mark just pointed out, the requirement that the ZX be in a metastable state requires that your limits are set at low values of epsilon and low values of the mass. But if we have other states that can be long-lived, the pseudoscalar, the scalar, the fermions, that could give us limits in different regions of parameter space. The other possible type of search is a search looking for invisible states, states which don't decay, but which might scatter through the same coupling that produces them. And there's a couple of experiments proposed, one at JLab, one at CERN. And these are motivated by the dark matter scenario, where your gauge boson decays to some invisible state. Again, we can have contributions to this from long-lived or stable states. Well, specifically long-lived states is a new contribution that might apply in this experiment, these experiments. Now, the details of the production I'm going to spend a little while going through, because they're not, I don't think they're that well known, at least among us. At least I had to spend some time figuring out how it works. The usual case that's considered is the on-shell gauge boson. That's the usual, and as it turns out, only relevant case. There's some subtleties associated with producing a hidden center through an off-shell gauge boson that I won't talk about. But the thing is, the target that's going on here, right, this is another sketch of what's going on. Electron comes and hits target, piece of clip art happens, and you produce a hidden photon. But the target is a very complicated thing. It has this, messy atomic electron cloud surrounding it. And as for what's going on in the nuclear structure, that's even worse. So what you do when you're faced with a complicated target is you write down some form factors, and more precisely you do the Weizsäcker-Williams approximation, which involves effectively thinking of this whole thing in the electron rest frame, where you have your target flying towards you, and it looks not like this complicated thing here, but rather like a still complicated cloud of virtual photons. But now you just need to write the form factors for this cloud of virtual photons, and you're done. And the requirement that this works, you need to be in some appropriate set of limits. So the gauge boson has to be much lighter than the energy of the electron beam, and it should also be much heavier than the electron mass, although most people sort of ignore this limit. And you also need to get small angular scattering. And then what happens is you can relate the full differential cross-section into the cross-section for electron-photon scattering times a form factor which looks something like this in terms of the mass of the gauge bodies we're trying to produce, getting cut off at high mass. And it's precisely defined as an integral over form factors that you could look up over the final state mass and over the energy transfer. T precisely being minus q squared, where q is the virtuality of the intermediate photon. The most important thing here is that small angle quasi-elastic scattering dominates. Okay? Small angle is sort of required, but it also turns out to be the most interesting, and of course the one that your experiment is able to measure because it's quite a small transverse size. Quasi-elastic, the factor of 1 over the virtuality squared here, points towards that. It's just the requirement that the photon be as close to being on shell as it can. The Weizsäcker-Williams approximation gives us an analytic expression for the differential cross-section, or more precisely, numerical expression once we factor in this thing here, which we convert. It also gives us the total number of gauge bosons that we will produce. We can convert that into the number of signal events by figuring out. Essentially what we did was we constructed a simple Monte Carlo to study the events. And they find the number of signal events as a product of the number of gauge bosons times the branching ratios for all intermediate decays that you're interested in, the probability that whatever your long-lived state is will decay within the decay volume, and the probability that its daughter particles will actually hit the detector. That's if you're looking at a visible search of the type of number 4. If you're looking for an invisible search, then you replace the last two factors with the probability that your state that is produced hits the experiment, and the probability that it will scatter. Now, briefly to say a few things. These are the experiments that I will show some limits for. 5 of these are the ones that have been done before, and the last one is the JLab search for invisible particles scattering in their detector. And these figures, the main thing I'll say here, most of this has been looked at as all of this was required to look at the previous things, such as the plot that I showed at the beginning of this section, except for this column here, the threshold energy of each experiment, which becomes very important in these more complicated decay chains. Whereas before you have gauge boson decays to a pair of leptons, the leptons carry roughly half the energy of the beam, and so you pass all of these cuts without any difficulty. But now we have gauge boson decays to something else, decays to electrons. The electrons carry a smaller fraction of the energy, and you now actually have to care whether or not you hit the thresholds. That multiple decay chain also relevant for these experiments here, which have been proposed to fill in the gaps in that parameter space, but unfortunately set no limits on these multi-step decay chains for the simple reason they impose the cut. That the energy of the electron and positron final states reconstruct the energy of the beam. That is the key cut they use to get rid of backgrounds, which simply isn't true when we have, for example, gauge boson decays to scalar pseudoscalar. For the same reason that we saw with the mesonic decay limits. This sort of also comes up to something that Marcus said a little while ago. The general structure of the exclusion limits is something like this. Below the electron threshold, whatever we produce can't decay to visible stuff, and so we won't see anything. Here, there's an upper bound which comes from the lifetime of whatever the state is too short, sorry. There's a kinematic limit when we can't produce the hidden sector. And then there's a cut off here. The cross-section is proportional to epsilon, more precisely to epsilon squared. And also the lifetime may become too long. Those two things can set the lower contour, the lower boundary on this exclusion contour. And almost all of the decay products will have this general structure, although in some cases it will cut off on the plot surrounded right here. This corresponds to epsilon about 0.1. So going through things, going through the results that we find out of all of this, we start with slopes A and B. So slope A, this is the situation where the gauge boson decays to a pair of electrons. And these lines here are the lines that I showed a few slides back. And for comparison, I've also shown the anomalous magnetic moment and anomalous magnetic moment of the electron and muon, those contours. And this red region here is the most constraining new limit that I find, coming from the production of an off-shell hidden production of the hidden sector through an off-shell gauge boson, with the scalar then decaying to a pair of electrons at some late time. It took me a long time to calculate this, which is unfortunate because, as you can see, it is entirely within this exclusion contour here, and therefore sets no new limits. A similar thing happens over here. This is the case when the gauge boson is decaying invisibly, and this is the limit that comes from the production of a scalar that decays visibly. The black lines are the lines, the exclusion contours that you expect from the JLab search for an invisibly decaying vector boson, with the different lines corresponding to different estimates of discrimination of signal over background. Since this is precisely the case that experiment is trying to probe, it's not surprising that it is a pretty good estimate in this case. Things get more interesting once we go to these other topologies. For this benchmark slope C, the gauge boson decays to a pair of scalars, and now we have exclusion contours which are stronger than ones that we've been found previously. So what's going on here? So first of all, the blue region. This region comes from the late decays of the pseudoscalar. The pseudoscalar, remember, has a three-body decay which is also suppressed by epsilon, so that is how it's long-lived. And those decays can remain sufficiently long-lived out to 10 to the minus 5 in epsilon and fill in this region here. Now, these limits are stronger, but they are also less robust in the sense that I could have slightly varied the parameters I chose to allow this state to decay to fermions while the scalar would be forced to decay to the standard model. And in that case, these limits would go away. I can also get a similar thing if I allow this pseudoscalar to decay to a pair of Higgs. This requires violating CP, but it can be done. So we also have the limits from the scalars. And here we have a difference between the limits in dark red, which is in the model that includes the Higgs mass mixing between the visible and hidden sector Higgses, and the lighter shaded region with a dashed boundary, which is where I turn that mixing off. And we see that the limits with the mass mixing are weaker than those without, which is because the lifetime is much shorter when I include the mass mixing, and so it ends up decaying too quickly. We also have in black some limits from the JLab search for invisible states, which comes, in this case, not from the actually stable fermion, but from the long-lived scalar. Finally, we have the slope D, which is where the gauge boson decays to fermions, and this is much simpler. We have no dependence on the Higgs mass mixing because all of the limits are coming from the long-lived decay of the fermion. And they fill in that general structure that I showed before. We have limits from E137 at SLAC, from a KK experiment from E774 at Fermilab. We have limits from JLab from scattering of the absolutely stable fermion, and they fill in some of the region that is preferred by anomalous magnetic moment of the muon, but not all of it. Okay, so 10 minutes, so let me just go through the final section of the talk.
So for these experiments, how boosted my mediator would be if it's like 1 GeV, for example? So you have an idea.
So E137, which is the most important one, the typical energy is around 20 GeV.
Oh,
I mean, basically, the energy is very nearly the beam energy, which is 20 GeV.
Mm-hmm.
So your gauge boson has that energy, and then its decay products will have appropriate fractions thereof, but roughly half for a one-step decay. So here, if you produce this state here, which has 10 GeV and will have a mass, it'll be less than GeV, so its boosting will still be about the same, a factor of 20 or so.
So the decay product would be pretty...
The decay products are fairly collimated, but the actual searches just look for one electron above the threshold, one electron specifically, or positron above the thresholds within the decay volume, and it points back towards the target.
Mm-hmm.
So the boosting is sort of relevant in ensuring that you don't have a state which goes up in this direction and then decays. That can happen, but it's very, very rare. Mostly it's all traveling in a straight line.
What's the relative, the size of the detector and the distance away from the detector? Is it,
so
does it cover...
there's a range of numbers here. Right?
I see.
This is the length of the shield, this is the length of the decay volume in meters. So E137, which sets the strongest limits, that's 280 meters, 380 meters. I can remember how to add. Compared to a transverse size of about 1.5 meters. Right? But then you have other experiments such as E774, that was just 2.5 meters between target and detector. Although none of these experiments are very large in the transverse size, because they are all looking for circles very close to the beam axis. Okay, proton searches are in some respects simpler in the sense that if you've been doing things with LHC, then you know how to calculate cross-sections of protons colliding with protons. There's also a number of previous searches. This is from the big review last year, which some of these beam experiments, such as CHARM, LSND, U70, were based on proton beams. There's also this search here. This is from Schuster et al., the paper that looked at gauge bosons decaying to scalars. And they found some limits in this region at somewhat higher masses, but this is the Higgs mass, so the vector gauge boson mass is a bit higher even than that. And at smaller values of the kinetic mixing, 10 to the minus 3, 10 to the minus 2, from one experiment, the CHARM beam dumping experiment. And a couple of other searches that are orthogonal. Now, the way you can produce this thing varies depending upon the mass scale of the hidden sector. If the hidden sector states are light, then they'll be producing the decays of mesons. Either, for example, a pion can decay to a photon, and then the photon, 2 photons, one of which kinetically mixes into the gauge boson. And this can also happen to allow you to produce an off-shell gauge boson into the hidden sector. Or, if the gauge boson itself is a vector, it will mix with the photon. This happens, for example, with the rho, very important. The photon then mixes to the gauge boson, and you can pair produce hidden sector states that way. Next, so relevant decays, pion goes to photon plus ZX, delta meson, delta resonance goes to ZX plus neutron, or rho decaying to a pair of hidden sector states, and also other pseudoscales in addition to the pion set limits that are important at masses above the pion mass. If the masses are high, then, as I stated already, it's just QQ bar goes to something. Heavy in this case means things need to be bigger than 1 or 2 GeV. You can kind of see, if you look at these plots of cross-sections, that as you get below that point, the difference between the the tree-level lines that are solid and the one-loop lines that are dashed are quite increasingly poor, given this is a logarithmic scale. and really quite poor if you look at this situation where I'm producing on-shell gauge bosons. It just looks horrible. This unfortunately gives you a bit of a problem with what you do between about, say, 2 GeV, where you can be more trusting of this approximation, and the mass of, say, the eta prime meson, which is about 800 GeV, 800 MeV, or the rho meson, about the same thing. It's kind of hard to fill in the gap. So what we did was we sort of pretended that we could trust these calculations down to that scale. And what you'll see is that they don't disagree with the results you get from Meson searches too badly. But that is a systematic uncertainty in that region that should be borne in mind. So there's a lot of searches here as well. In particular, all of the neutrino experiments can set limits, at least in principle. LSND, for example, we have various searches from T2K, Ingrid in particular, Minos, as well as dedicated beam type experiments like CHARM and the new calorimeter I at U70 experiment. And also other experiments too that people have used to set limits that won't set interesting limits on our model. There's even possible future limits from Project X and after LHC, but we don't have results for those. In particular, in the case of this after LHC, I don't have enough details, but I don't think they will be relevant to our model.
What is that? I've never heard of it.
It's a proposed fixed target experiment. I think it's a fixed target experiment something. As you can see, it's still quite speculative. Actually, I think the R might be the R experiment. So when you put all of this together, the limits that you get, and I'm running short on time, so I'll be brief, but it's not too hard to figure things out. These are the same plots that I've shown before with kinetic mixing and gauge boson mass. I'm also showing the Higgs mass, since that is the state that is long-lived, and I have the space. And on the left, we have the situation where I where I include the mass mixing, and on the right, without it. And we have the previous limits that arise when the gauge boson decays to leptons, and we have a load of new limits up here. In particular, these limits come from the CHARM experiment, decaying either to pseudoscalars or mesons, or through QQ bar in this higher mass region. We also have prospective limits, in particular from Minos, Ingrid. These are these limits here, these neutrino experiments can potentially set fairly good limits in this mass region here. And similar things show up if you go at the invisible searches. Again, you can see the rho. I didn't draw attention to it. This is the rho meson. You can see the resonant peak there is quite strong. Shows up here as well if the thing is decaying invisibly. This is coming again from visible decays of the scalar. We also have very good limits in this case from the neutrino experiments, prospective limits, and also from LSND coming not from decays but from scattering, which looks a bit like a neutrino. So although there's an uncertainty based on knowing the neutrino flux, you can still set fairly good limits from those experiments. When the gauge boson decays to scalars, the limits get very, very good relatively from this type of thing, because now we're producing an on-shell stuff through on-shell decays. If you compare this limit here, this is going up to 10 to the minus 3, and in this case it's going up to 10 GeV in case of the gauge boson mass, compared to the limits you had here, going up to a couple of GeV and a few times 10 to the minus 3. And again, limits from neutrino searches, limits from LSND. This plots just show the limits that come from long-lived scalars, long-lived Higgses. The limits from the pseudoscalar are somewhat different and are shown here, and they extend again. They extend down to lower values of the kinetic mixing, 10 to the minus 5. There's the rho meson. We see here this is a clear sign of the difficulties involved in maxing the high energy and high mass and low mass limits. But it's not too important because the limits from another experiment are actually somewhat stronger. This is the red is the CHARM experiment, and blue is the U70 new calorimeter I experiment. And finally, the limits from fermions. Again, it's all very much the same kind of thing, with just the precise limit way, but the exclusion contour varies. You then put all the limits together, and that's where things get a little bit more interesting. Let me start with benchmark slope A. This is the most well-studied case where the gauge boson decays to a pair of leptons. And indeed, most of the limits on this plot are ones we've seen before. We have the previous limits from electron beam dump experiments in blue, also this limit here that I didn't talk about, but this comes from the Miami and Apex experiments. The limits from charm and similar hadronic beam dump experiments in red. So the bar limits, the limits from anomalous magnetic moment of the muon. But in red here, these are the limits in this experiment, the charm experiment, beam dump experiment, coming at low masses. And if you look at this green shaded region here, that is the region where this can explain the discrepancy in the anomalous magnetic moment of the muon. And these new limits fill it in almost entirely that preferred region. There's a tiny little gap there that's not quite filled in. And this, I should point out, this requires you have a Higgs in the spectrum that decays visibly. But if you do, then that seems to put this under a lot of pressure that you can use this model to explain this discrepancy. If we go to benchmark B, something similar happens. We have all of the previous exclusion contours, and then we have the new results which come from the charm experiment and from LSND, and they completely fill in this region that would explain the magnetic moment of the muon. For benchmark C, these are the first bits you can set on this model beyond, there was the one previous search which basically lived here, but everything else is new, and again, the preferred region for the anomalous magnetic muon is completely filled in. And finally, the situation where the gauge boson decays to fermions, these are the first time that we have limits in this case. We have the limits from gauge boson from proton beam dump experiments in red, from electron beam dump experiments in blue. There's the bar limits. And this time we do actually have a small region that has not been ruled out, because in this model, the Higgs decays invisibly, so it doesn't give us any limits. The yellow line is the prospective limits from the JLab experiment, and we see that they will probe this completely. The green dash is the limit from Ingrid, the neutrino experiment of T2K. When it's finished taking data, it will also probe this region here. But at the time being, this model still lives as a possible explanation for that discrepancy. So, to finish and summarize, hidden sectors where we have a coupling through gauge kinetic mixing have a richer phenomenology than is usually considered. And we have a simple, in the sense that it's minimal model, that illustrates this and covers these four categories of decays that I discussed. The limits when the gauge boson can decay to either scalars or fermions in the hidden sector have been much expanded or are completely new compared to what has been done before. And finally, we see that it is difficult to explain this muon anomalous magnetic moment if our hidden vector is Higgsed and the Higgs decays visibly. And with that, I'd like to thank those of you who decided to stay and finish.
Just have a question. So for some of the experiments that use a resonance condition, are do they have a very high background that's really being suppressed by the resonance condition, or is it?
Yeah, I think that's part of it, but more to the point is the way they set the experiment up. Let me think for a moment. No, that's wrong. No, it is. It's the background, because those experiments actually work a little differently, most of them. They don't have a large shield to block out the background stuff. In fact, their detectors are fairly close, because they are probing, they're probing this region here. These yellow lines are those prospective limits all combined together. And remember that the reason why these limits got cut off was because these hidden sector was decaying too quickly, the hidden vector. So they are looking for stuff that decays quite quickly, so they don't need a large shield. But then they need some other way to discriminate from the background, and that is what they use the resonance, the requirement, they reconstruct total energy to discriminate.
I was just wondering that if you focus on the forward region, if you have some specific model for a decay that does involve an invisible particle, if you focus on the forward region, you may have a theoretically calculable distribution of masses, right? So you wouldn't have a peak, it won't be a peak, but it will be some distribution that you can calculate. And so, but if you're really using the peak as a background subtraction, and subtracting a lot of background, then I would guess that won't be useful. So I was just wondering whether you could somehow use you could still get some limits from those experiments.
That's
knowing, for a given hypothesis for if you had a simple hypothesis for the decay.
Actually, again, they don't look for a peak in the invariant mass distribution. They look for the when they do. But their first cut is the total energy of the two states they measure is the beam energy. Right. So, and that cuts down a lot of the background. And I think the problem is if you don't have a large coverage, which these experiments don't have, then the possibility of E plus E minus and missing energy could be E plus E minus photon when you miss the photon, and that's not an uncommon QED process. So you would need some other way to think about getting around those constraints. Now there are some. You will still be able to do some stuff based on. Sorry. I'm getting mixed up. The invisible searches, they work fine, but the visible searches are just problematic.
So I have a quick question. So for explaining the muon magnetic moment discrepancy, does it matter that this Z prime is GV scale is light, or does it also work if it's, say, above the Z or TV scale?
If it's very heavy, I guess.
Just because I have curiosity. Does it work anyway, or?
Well, I guess they're presumably well. In principle, right? All you need to do is crank up the coupling.
Yeah. So there's no other.
But
there's
then
no sign from the mixing the Z or.
No.
Okay, it's just a script. Okay, so then. Okay.
I don't think so anyway. Although that, I would have to check.
Okay, fine.
Is really the answer.
Sure. Thank you. Are there other questions? Okay, if not, let's thank Andy again.